A 300-meter ship falls into a hole in the sea. Bow and stern ride water. The middle rides nothing. Steel that long stops being a box and becomes a beam, and beams break. On 1st January 1995, a laser beneath a North Sea platform measured a wave 25.6 meters tall, inside a sea running about 12. Engineers had spent a century calling that impossible. 17 years earlier, the München vanished with 28 men. Ships survive big water by bending, and by being longer than the wave. So why do they fold in half? Usually the wave is not the answer. Start with the thing nobody tells you about big ships, because everything else in this story depends on it. A loaded bulk carrier is not a boat in any sense your intuition understands. It is a hollow steel girder, 300 meters long, roughly 45 wide, with sides about as thick as the spine of a paperback, 20 millimeters of plate, 30 in the heavily worked areas. Scale that against her length, and the proportions become genuinely absurd. An eggshell is a thicker skin relative to the egg than a ship's hull is relative to the ship. The reason the thing does not simply crumple is not the plate. It is the shape. A long box beam is enormously stiff in bending as long as its top and bottom stay flat, straight, and continuous. The deck is the top flange. The bottom shell is the bottom flange. Everything the ship does structurally, it does by keeping those two surfaces honest. Now load her. Iron ore in alternate holds, because ore is dense. And filling every hold would put the center of gravity too low and make her roll like a hammer. So the weight goes in as a series of concentrated lumps with gaps between them. Buoyancy, on the other hand, does not care where you put the ore. Buoyancy pushes up according to the shape of the underwater hull, distributed smoothly along the entire length. Weight goes in lumps. Support arrives smoothly. Those two things do not cancel out, and the difference is a bending load that exists before the ship has left the berth, before the weather forecast matters, before anybody has looked at a chart. Naval architects call it the still water bending moment. It is the load the ship carries in a flat calm on a windless morning. And on a big ore carrier, it can be tens of thousands of ton-meters of permanent structural stress sitting there, doing nothing, waiting. Then you put waves under it. Here's the part that takes a moment to see properly. When a crest arrives under the middle of the ship, the ends are hanging over comparatively empty water. The middle is pushed up. The bow and stern sag. The deck stretches, the bottom compresses, and the whole hull tries to arch. Sailors call this hogging. Half a wave later, the geometry inverts. Crests under bow and stern, a trough under the middle, the ends lifted and the middle unsupported. Now the deck is being squeezed, and the bottom is being pulled. That is sagging. Hogging, sagging, hogging, sagging. And the interval between them on a long ship in an ocean swell is somewhere around 6 or 7 seconds. Do the arithmetic on that, and it stops being an abstraction. A full reversal every 6 or 7 seconds, roughly 9 a minute, 500 an hour, 13,000 in a day of bad weather. Hull fatigue is designed against something on the order of 100 million wave load cycles across a working life. 100 million flexures of a structure the length of 3 football pitches, each one pulling on every weld, every hatch corner, every place where a designer changed the thickness of a plate. The hull is designed for that. It is designed for far worse than that. Classification societies size the structure against a wave load statistically expected once in 20 years of North Atlantic service, and then they add margin on top. Which raises the question this entire story exists to answer. If the design case is a 20-year wave, and the margin sits above the design case, the main case is, how does a modern ship in a survivable storm end up in 2 pieces with her crew in life rafts? The first answer is disarmingly simple, and it is the answer most people stop at. A ship survives a wave largely by being longer than it. A 300-meter hull in a 100-meter swell spans 3 crests at once, and the loads average themselves out. The sea can be violent, and the girder barely notices because no single crest has enough length to lift the middle and abandon the ends. Length is protection. That is real, and it is most of the reason enormous ships routinely cross oceans that would destroy small ones. So the dangerous wave is not the tallest one. The dangerous wave is the one whose length matches the ship. Deepwater waves obey a fixed relationship between period and length, about 1.5 times the square of the period, in meters. Run the numbers for a 300-meter ship, and the wave that fits her exactly has a period of roughly 14 seconds. Not a freak, not a monster. 14 seconds is an ordinary long swell, the kind that arrives in the western approaches after a low has crossed the Atlantic, the kind a passenger would describe as a gentle rise and fall. It is the sea state in which the ship stops averaging anything and starts being loaded exactly the way a laboratory test rig would load a beam it intended to break. And that is the mechanism sitting underneath every incident in this story. Not size. Fit. Which brings us to the only stretch of ocean on Earth where the geography deliberately manufactures that fit, and where somebody sat down and proved it with a list of dead ships. Look at the southeast coast of South Africa. Warm water leaves the tropical Indian Ocean, runs down the Mozambique Channel, gathers itself against the African continental margin and becomes the Agulhas Current, arguably the largest western boundary current in the world ocean, moving something on the order of 70 million cubic meters of water per second. That number is meaningless until you convert it. It is more than 50 times the combined flow of every river on the planet, all of it going the same direction, all of it warm, all of it pressed into a core about 34 kilometers wide. Squeeze that much water into that narrow a channel, and it accelerates. Mean peak surface speeds in the core run around 1.36 meters per second, and off the southeast coast the current has been measured at up to about 2.5 meters per second, 5 knots. For a ship, 5 knots of favorable current is not a curiosity. It is money. It is a full day saved on a Durban-Cape Town leg, thousands of dollars of bunker fuel unburned, a berthing slot kept, a charter clause satisfied. Remember that, because it explains everything about why ships keep going there. The second thing about the Agulhas is where it sits. Most great ocean currents run out in open water where nobody has to interact with them. The Agulhas hugs the edge of the continental shelf, frequently within 20 to 50 kilometers of the coast, following the 200-meter depth contour, like a road, following a ridge. Mariners of the old school called that the 100-fathom line. On a chart, it is a thin curve of soundings. In practice, it is the boundary between a shallow shelf and a seabed that drops away into deep ocean, and the current sits on top of it because that is where the topography steers it. Now bring in the weather, because the current alone does nothing dangerous. South of Africa, there is no land at that latitude. Nothing between the Cape and Antarctica but water and the westerlies, and the Southern Ocean generates swell, the way a factory generates product, continuously at industrial scale, propagating northeast for thousands of kilometers and arriving on the South African coast as long, heavy, southwesterly swell. The Agulhas Current also runs southwest. The swell is going one way, 4 or 5 knots of water is going the other, directly against it. What happens next is not exotic physics. It is the same thing that happens when you shorten a spring while it is oscillating. Wave energy propagating into an opposing current gets compressed. The wavelength shortens. The wave has nowhere to put the energy it is carrying except vertically, so it grows taller and steeper. Push the opposition far enough. When the current speed climbs toward roughly a quarter of the wave's own propagation speed, and the wave stops advancing altogether. It piles into itself. Energy accumulates in a shrinking amount of water. Add the second effect, which is worse and less obvious. A current with a fast core and slower edges bends waves the way a lens bends light. Swell entering the current obliquely gets refracted inward, toward the fast axis. Energy that started spread over a wide front gets concentrated onto a narrow band of sea. The current is not just steepening the waves, it is collecting them. So take the ordinary long southwesterly swell out of the Southern Ocean, say a 14-second sea, exactly the period that fits a large ship, and drive it into a 5-knot opposing jet that also focuses it. The result is not a taller version of an ordinary wave. It is a wave with a shortened, steepened face, and immediately ahead of it, a deep and unnaturally wide trough. Survivors describe that trough consistently across a century of accounts and multiple nationalities, and always in the same words: a hole in the sea. Sail a long ship into a hole in the sea, and the physics you just learned takes over. Bow drops into the trough. Stern is still on the previous crest. The middle is unsupported. The still water-bending moment is already loaded. The wave-bending moment adds on top, and then the bow, having fallen, meets the steep face of the next crest coming at it. Somebody worked this out, and he did it the hard way, by counting wrecks. John Kennaway Mallory was a master mariner, a South African Navy officer, and professor of oceanography at the University of Cape Town, which is an unusual combination and exactly the right one. In 1974, he published a study in the International Hydrographic Review examining abnormal waves on the southeast coast of South Africa. He did not begin from theory. He began from casualties. Vessels damaged or destroyed along that coast over the preceding 2 decades, and he plotted where each one had been when it happened. The dots did not scatter. They clustered. They clustered along the 100-fathom line in the vicinity of the shelf edge. They clustered near submarine canyons cut into that shelf edge, where the underwater topography distorts the current and sharpens the focusing. And they clustered in time with the approach of a cold front from the west. The frontal weather that puts strong southwesterly wind and fresh southwesterly swell into the teeth of a southwest flowing current. 3 factors: the shelf, the canyons, the front. Line all 3 up, and the sea in that corridor manufactures the exact wave that fits a large ship, in a place large ships have every commercial reason to be. That is the difference between bad luck and a trap. Bad luck does not produce a map. Mallory produced a map, and the practical instruction that came out of it was almost insultingly simple. Stay inshore of the 200-meter line. When a front is coming through, give up your free 5 knots, accept the delay, and the mechanism cannot reach you. Ships kept using the line anyway. They still do. And 6 years before Mallory published, one of them came apart out there in a way that made the argument for him. The World Glory was a steam tanker, built in 1954 by Bethlehem Steel, 736 feet long, 4,179 tons deadweight, in tons. In June 1968, she was carrying 334,043 barrels of Kuwait crude oil, loaded in the Persian Gulf and bound for Huelva, on the southwest coast of Spain. Ask why a tanker was taking Kuwaiti oil to Spain, the long way around Africa, and you get the first piece of context that actually matters, because it is not seamanship. It is politics. Egypt closed the Suez Canal on 6 June 1967 at the start of the Six-Day War, and it stayed closed for 8 years. Overnight, every barrel of Gulf crude headed for Europe had to go around the bottom of Africa. Traffic on that route did not increase gradually. It was diverted, in bulk, in a matter of weeks, and it stayed diverted until 1975. The tankers got bigger to make the extra distance pay. This is the closure that produced the VLCC, and all of them, every single one, had to come down the Mozambique Channel and pass the Natal coast. The Agulhas Corridor did not become more dangerous in 1967. It became far more crowded. The mechanism Mallory would map 6 years later was already there, doing what it does, and the world had just redirected a significant fraction of its oil traffic straight through it. On 13th of June 1968, the World Glory was about 65 nautical miles east-northeast of Durban. The weather on record for that position is specific and unremarkable for the season. Southwesterly gale force winds, overcast, heavy swell, poor visibility, a front coming through from the west. Exactly the third of Mallory's three factors, lined up with the other two. Nothing about that morning required a decision anyone would call reckless. A loaded tanker in a southwesterly gale off Natal is a ship doing its job in weather it was built for. The crew would have been doing what crews do, reducing speed if the motion demanded it, checking the deck, keeping the ship's head in a manageable relationship to the sea, waiting the front out. She was 14 years old, which for a well-maintained tanker in 1968 was middle-aged, not decrepit. Then the sea did the thing the current makes it do. The accounts describe two very large waves arriving in succession, estimated at around 70 feet. Estimates from a deck in a gale are estimates, and nobody was holding an instrument. So treat the number as an order of magnitude rather than a measurement. The point is not the height. The point is the geometry. Two of them, back to back, into a 736-foot hull already loaded to her marks with crude oil. She broke in two. Read that sentence slowly, because it contains the thing that separates this story from a normal shipwreck. The World Glory did not fill up and go down. She did not capsize. Her structure failed, and the failure was the casualty. One moment there was a ship. A short time later there were two independently floating objects, both on fire, both leaking crude, with the crew distributed between them according to nothing more than where they happened to be standing. The stern section sank in about 2 hours. The bow section stayed afloat and drifted southwest, carried away, with grim neatness, by the same Agulhas current that had just helped destroy the ship. Rescue is where the numbers stop being abstract. 10 of the 34 crew survived. Contemporary press accounts at the time reported 4 dead and 22 missing, which is the shape of information in the first 48 hours of a marine casualty and does not reconcile cleanly with the final figures. The sources disagree, and the disagreement is worth stating rather than smoothing over. What is not disputed is that roughly 2/3 of the people aboard did not come home in daylight, 65 miles from a major port, in a heavily trafficked shipping lane. In 1968, 65 miles is nothing. A helicopter can cover it. A ship can cover it in 3 hours. The distance was never the problem. The problem was that men went into the water among burning crude oil in a gale, from a vessel that had gone from intact to bisected without an interval in which anyone could prepare, and the window in which a person survives that is measured in minutes. The cargo eventually went into the Indian Ocean, all 334,043 barrels of it. The initial official assessment was that the Agulhas current would keep the oil safely offshore. The current that concentrated the wave energy was expected to dispose of the evidence. It is a small detail, and it tells you how the entire system was understood at the time. The current was a fact of navigation, a thing that moved water and oil around, not a machine that built waves. So what actually killed the World Glory? The sea or the ship? That question has never been settled, and anyone who tells you it has is selling something. One reading is straightforward. An abnormal wave of the type the Agulhas corridor is known to produce imposed a bending load beyond the hull's ultimate strength, and the hull did what beams do. The other reading points at the ship. 14 years of cyclic baying loading in a hull from the first post-war generation of large all-welded tankers, and the possibility that the structure was already compromised before the wave arrived. Both readings are defensible from the available evidence. Neither can be proven, because the ship is on the bottom and nobody has ever gone down to look. The honest answer is that it is almost certainly not a choice between the two. That is the idea to carry forward, because it turns out to be the shape of every case in this story. A hull that would have survived that wave when new. A wave that would not have broken that hull when new. Both statements true and neither one sufficient on its own, which forces an uncomfortable question about the steel itself. And to answer it, you have to leave the Agulhas entirely, go back a quarter of a century, and stand on a dock in Oregon on a cold morning where there was no wave at all. Before that, though, notice something about how people used this coast before it started killing tankers. The Agulhas Corridor has been navigated for well over 500 years. Bartolomeu Dias rounded the Cape in 1488, and the Portuguese named it the Cape of Storms, before commercial optimism renamed it. The India route ran past this coast for 3 centuries under sail, and sailing masters developed an entirely practical relationship with the current that had nothing to do with theory and everything to do with not dying. A sailing ship could not hold a precise line along the shelf edge in a gale. She went where the wind allowed. Working eastward against the Agulhas, masters deliberately stood inshore of the current axis to escape the adverse set, into shallower water on the shelf, which, without anyone knowing why, put them out of the corridor where the focusing happens. Coastal traders in the region operated the same way for the same reason. The water inside the 200-meter line is slower, and slower water is where you go when you cannot afford to fight. The knowledge was not folklore. It was an operating rule, held by people who worked the coast continuously and who observed one thing modern deep-sea navigation has almost no way to notice: that the sea in one particular band of water behaved differently from the sea 2 miles either side of it. South African sailing directions and local practice have carried a version of that instruction ever since. In adverse conditions, keep inshore of the 200-meter line. Mallory's 1974 paper did not discover this. It quantified it and attached a casualty list to it. And here is the reversal that runs underneath the entire 20th century in this corridor and in every other one in this story. The engine did not just make ships faster. It made a line on a chart into something a ship could actually hold. A sailing vessel takes what the wind gives. A motor vessel takes the route that pays. Once ships could steer a course independent of the weather, the current axis stopped being a hazard to be avoided and became an asset to be harvested. 4 to 5 knots of free speed, available to anyone willing to put their keel over the shelf edge. Half a day. A tide at the pilot station. A charter deadline met. The technology that gave crews the power to escape the dangerous water is the same technology that gave them a commercial reason to sit in it. That trade is not stupid, and this is worth being clear about because there is a lazy version of this story in which everyone involved is an idiot, and the answer is that they should have gone around. The overwhelming majority of transits through the Agulhas Corridor are completely uneventful. A master who routes inshore of the 200-meter line every time, in all weather, will spend a career burning extra fuel and arriving late in exchange for avoiding a hazard that will probably never materialize on any given passage. The people making these decisions are balancing a small probability of catastrophe against a certainty of cost on someone else's timetable, with imperfect information about what the sea is doing 40 miles ahead. That calculation has never been solved. It has only been made faster with better data, by people under more pressure. Which brings the story to the steel, and to the moment when a brand new ship in a river, tied to a dock, with no wave anywhere near her, tore herself nearly in half in front of witnesses. Swan Island, Portland, Oregon. 16th of January, 1943. The Kaiser Yard had just finished a T2 SEA-1 tanker named Schenectady, and she had come back from her sea trials the previous day with everything working. She was moored at the fitting-out dock on the Willamette River, floating in flat fresh water, with no cargo, no crew at sea, no weather worth the name, and the open Pacific 100 miles downriver. Late in the evening, she broke. The noise was audible for at least a mile. The crack opened just aft of the superstructure and ran down through the deck and down both sides of the hull almost to the keel, and then the keel itself fractured. The middle of the ship jackknifed upward out of the river, while the bow and stern sagged down until they were sitting on the bottom. Only the bottom plating was still holding her together, and it was holding a shape that no longer resembled a ship. There was nothing to blame. That is the entire significance of the Schenectady, and it is why she is still taught in engineering schools 80 years later. Every explanation available for a ship breaking in half required a C. She had not been in one since the previous afternoon. She was tied up in a river in Oregon in January, and she came apart because of what she was made of and how she had been put together. Two things had happened, and they compounded. The first was welding. Before the war, merchant hulls were riveted, and riveting has a property nobody had thought of as a safety feature until it went away. A riveted hull is not one piece of metal. It is thousands of overlapping plates, and every joint between them is a discontinuity. Start a crack in a riveted plate, and it will run until it reaches the edge of that plate, and then it stops, because there is no continuous path for it to follow. Every seam is a crack arrestor by accident. Welding was the innovation that made wartime shipbuilding possible. It was faster, cheaper, lighter, and it allowed a yard to assemble a ship from prefabricated sections in a fraction of the time riveting demanded. The whole Liberty ship program depended on it. What welding also did was turn the hull into a single continuous piece of steel from stem to stern, with an uninterrupted path from any point to any other point. A brittle crack in steel does not creep. It travels at a substantial fraction of the speed of sound in the material, thousands of feet per second. 300 meters of ship is crossed in a fraction of a second, which means there is no interval in which a human being can perceive it, decide anything, or act. A ship in that condition does not develop a problem. It arrives at the end state directly. The second thing was the steel itself, and this is where a metallurgist in Cambridge changed the industry. The plate being produced for wartime hulls had a chemistry that nobody at the time recognized as dangerous. Sulfur content too high. Manganese too low. Steel like that has a property called a ductile to brittle transition temperature. Above it, the metal behaves the way you expect metal to behave. Put too much load on it, and it stretches, yields, deforms, tears slowly, and gives you visible warning that something is wrong. Below it, the same steel stops tearing and starts shattering. It behaves less like metal and more like glass. Constance Tipper, working at Cambridge, Statuary Workes Cambridge, established this and made it measurable. She demonstrated that there is a critical temperature at which the fracture mode of a given steel changes over, and she developed the test, still in use, still bearing her name, that identifies where that temperature sits for a particular batch of plate. What her work exposed was that the wartime hulls were being sent into the North Atlantic in winter with steel whose transition temperature was above the temperature of the water they were floating in. The ships were not overloaded. They were cold. Put the two together, and you get an epidemic. Across the wartime program, there were roughly 1,500 instances of significant brittle cracking. 3 Liberty ships broke completely in half without warning. Some of the casualties happened at sea, in weather, and looked like ordinary storm losses, which is precisely why the Schenectady mattered so much. She failed in front of witnesses, in daylight conditions of complete calm, and removed every alternative explanation. There was a third contributor, smaller but instructive, because it recurs later in this story in a much more modern form. The cracks tended to start in the same places: square hatch corners, the ends of welded seams, the sharp internal angles where a deck opening interrupts the continuous plating. Any abrupt change in geometry concentrates stress at the corner. A square cutout can multiply the local stress by a factor of 3 or more compared to the surrounding plate. The designers had drawn square corners because square corners are easy to draw and easy to cut. Nobody had connected the drawing office to the fracture mechanics because in 1941 the fracture mechanics did not yet exist. The fixes came quickly and they worked. Hatch corners were rounded, riveted crack arrestor straps were installed across the deck, and sheer strake of ships already in service, deliberately reintroducing the discontinuity that welding had removed. A crack running along a welded deck hits a riveted strap and stops. Steel specifications were rewritten with controlled manganese and sulfur, and with actual notch toughness requirements. Welding procedures were brought under inspection. Within a few years, the epidemic was over. The Schenectady herself was repaired and went back into service in April 1943. And here is the thing that should bother you, because it bothered the naval architecture profession for the next 4 decades. Fixing brittle fracture did not stop ships breaking in half. It changed how they do it. Once the steel would reliably tear rather than shatter, and once the geometry stopped concentrating stress at square corners, the sudden crack failure mode largely disappeared from the casualty record. What replaced it is slower, more local, and much harder to see coming because it does not announce itself with a noise you can hear a mile away. The new failure mode is buckling. Think again about the hull as a beam, with a deck flange on top and a bottom shell flange underneath. In a hogging condition, the bottom shell is in compression. In sagging, the deck is. A steel plate in tension is extremely strong and fails only when you genuinely exceed its strength. A steel plate in compression is a completely different animal. It does not need to be overstressed to fail, it only needs to become unstable. Push a long, thin plate hard enough along its length and it will not crush. It will suddenly bow sideways out of plane, and the instant it does, it stops carrying the load it was carrying. And everything it was carrying transfers to the plates on either side of it, which are now overloaded, and buckle in turn. Buckling propagates, not at the speed of sound, but fast enough that the outcome is the same. A localized instability in a few plates of bottom shell becomes a collapsed section of bottom shell, which means the beam has lost its bottom flange, which means the beam has lost most of its strength in a fraction of a second, and then the hull simply folds around the failure. This matters enormously for the rest of this story, and here is why. Brittle fracture was a materials defect. It could be fixed by changing the material, and it was. Buckling collapse is not a defect at all. It is a property of thin plates in compression, and every efficiently designed ship in the world has thin plates in compression, because the entire art of naval architecture is putting steel exactly where it is needed and nowhere else. The stronger the design method, the closer to the limit the design sits. You cannot metallurgy your way out of it. The only defense is knowing accurately how much load the hull will actually see. And that is a question about the ocean, not about steel. Which is why the World Glory is such an awkward case, and why the argument about her has never resolved. She was launched in 1954. She was built after Tipper, after the crack arrestors, after the steel specifications were rewritten. Whatever happened to her off Durban was not the Schenectady's problem in a warmer ocean. She was a post-fix ship in a documented gale, in a corridor that concentrates wave energy, and she came apart anyway. By the middle of the 20th century, the profession had a strong hull, good steel, and a design wave. What it did not have was any way of knowing whether the design wave was actually the biggest one out there. And every time a ship disappeared in deep water with all hands, the evidence that might have answered that question went to the bottom with her. To understand why the ocean kept winning that argument, you have to look at what a wave actually does to a ship's bow in the 1/10 of a second after it hits. A modern bow is flared. It widens as it rises, so that the hull gains buoyancy quickly as it goes down into a wave, and lifts rather than burying itself. It is a good design. It also means that when a ship pitches hard, an enormous, rapidly increasing area of steel gets driven into solid water at a relative vertical speed of several meters per second. Two things happen at that instant, and they are different problems. The first is the impact itself. Naval architects call it slamming, which is exactly the right word because it is the sound the crew hears. In heavy-head seas, the bow rises until the forefoot comes clear of the water, hangs there for a moment, and then comes down. Water is not compressible. Flat steel meeting flat water at speed generates local pressures measured in hundreds of kilopascals, applied over a few thousandths of a second, over an area of hull plating that may be tens of square meters. That is a local structural problem. It dents plating, it cracks welds, it damages bow structure, and it is survivable and well understood. The second thing is the one that kills ships. The impact does not just push on the bow. It rings the entire hull. A 300-meter steel girder has a natural vertical bending frequency, the same way a tuning fork does, and a slam excites it. After each impact, the whole ship vibrates in bending, bow and stern moving in one direction while the middle moves in the other, at a frequency of roughly 1 or 2 cycles per second, decaying over the next several seconds until the next slam sets it off again. That is whipping. On the bridge, it registers as a boom, followed by a shudder that runs the length of the vessel and rattles anything not secured. Crews describe it as the ship complaining. In accommodation aft, you feel it come up through the deck plating into your feet. Now put the two loads together, because that is the entire point. The slow, wave-induced bending moment builds and releases over the wave period, say 10 to 15 seconds. The whipping vibration cycles roughly 10 times faster, which means that at some moment, in some slam, the peak of the fast vibration lands exactly on top of the peak of the slow wave load. The two add. Studies of full-scale measurements on large ships put the high-frequency contribution to peak vertical bending moment in the tens of percent, and it rises as the waves get bigger. Read that again. The worse the weather gets, the larger the fraction of the hull's total load comes from a mechanism that classification rules, for most of the 20th century, did not explicitly account for. There is a related and quieter version of the same effect called springing, where ordinary short waves keep the hull's natural frequency continuously excited at low amplitude. Springing does not break anything on a given day. It accumulates fatigue in the structure, at a rate that stress calculations based on wave loads alone will underestimate, which means the ship arrives at any future overload event with less strength than the paperwork says. The defense against all of this is simple, and every master knows it. Slow down and change heading. Reduce speed, and the relative impact velocity falls, and slamming pressure scales roughly with the square of that velocity, so cutting speed by a third cuts the impact energy dramatically. Alter course, and you change the encounter period so the ship is no longer meeting waves at the interval that fits her. Both cost money. Slowing a container ship by 4 knots across an ocean is a missed berth window at the far end, and a cascade of consequences through the schedule. Altering 30 degrees off track adds miles and fuel. Neither decision is ever taken with certainty, because the master is trading a definite operational cost against an indefinite structural risk. Based on his reading of a sea he can see for perhaps 2 miles in the dark. And that was the state of knowledge in December 1978. Good theory about how hulls bend. No ability whatsoever to measure what the ocean was actually doing to them. And an institutional conviction that waves above a certain size simply did not occur. Then the München went missing and left behind exactly one piece of physical evidence. She was not an old ship or a marginal one. Built in 1972, 261 meters long, she was among the most advanced cargo vessels afloat, a lash carrier standing for lighter aboard ship, a design that solved a genuine commercial problem. Ports cost money and take time. A lash ship carries her cargo in floating barges, called lighters, which she lifts aboard and sets down with an enormous gantry crane that travels the length of the deck. She can arrive off a river mouth, put her lighters in the water, pick up the loaded ones waiting for her and leave, without ever entering a port or paying for a berth. The München carried 83 of them. She left Bremerhaven on 7 December 1978, loaded with steel products in her lighters, bound for Savannah, Georgia. Crew of 28. A North Atlantic crossing in December is not an adventure. It is a scheduled commercial operation performed thousands of times a year, and the ships that do it are built for it. The weather that month was severe, which in the western approaches in winter is the normal condition and not a warning. Nothing in the record suggests the München reported difficulty, requested assistance, or deviated. She was 6 days out, roughly 450 miles north of the Azores, and by every indication she was doing exactly what she had been built to do. In the early hours of 13 December, radio stations began picking up fragments. The French coastal station at Bordeaux-Arcachon logged a distress call at about 3:10 in the morning. What came through was Morse, and it came through broken, pieces of a mayday, not a message. Reports from the period indicate transmissions referring to severe damage and a heavy list, and this is where the record has to be handled honestly. The transmissions were fragmentary. The reconstruction that has her drifting for many hours at a list around 50 degrees without power is an interpretation of incomplete evidence rather than an established fact, and no confirmed transmission ever established what actually happened to her. What is not in doubt is the search. It was, at that time, the largest peacetime sea search ever mounted. 110 ships and 13 aircraft from multiple nations, working an area described as 5 times the size of Germany, in a December North Atlantic that did not improve for them. Consider what that actually involves. Aircraft flying visual search patterns below cloud and gale conditions, looking for objects a few meters across in a sea running 12 meters and covered in whitecaps that look exactly like a life raft from 800 feet. Merchant ships diverting off their tracks and steaming into the weather to run parallel search legs, burning fuel, arriving hours or days after the event with a drift estimate that widens every hour. Every additional hour makes the search box bigger and the probability of detection inside it smaller. Rescue arrived. Rescue arrived in overwhelming force. It found nobody. That is a distinction worth sitting with, because it recurs in every case that follows, and it is the one people find hardest to accept. The failure was not a failure of response. The response was extraordinary. The failure was that whatever happened to the München happened faster than the interval between a distress signal and the arrival of help, and no amount of ships and aircraft compresses that interval below the speed of the event. On 16 February 1979, more than 2 months later, the car transporter Don Carlos recovered something. It was a lifeboat from the München's starboard side, and it was the way it had been damaged that made it important. The pins that secured the boat to the ship had been twisted, and the direction of the twisting indicated a force applied from below and aft, water driving upward against the underside of the boat with enough violence to tear it off its mountings. That boat had been stowed roughly 20 meters above her waterline, 60 feet, 6 stories. Spray reaches 60 feet routinely. Spray does not shear steel davit pins. Something with the mass and coherence of solid water reached 6 stories up the side of a 261-meter ship and applied enough force to strip a lifeboat off a vessel built to survive the North Atlantic in winter. The German investigation had a problem, and it is a genuinely interesting problem rather than an act of institutional cowardice. Their models said this could not happen. Linear wave theory treats the sea surface as the sum of many independent components, which produces a specific statistical distribution of wave heights. And in that distribution, a wave large enough to do what the lifeboat evidence implied was so improbable that invoking it looked like bad science. Faced with physical evidence that contradicted the accepted mathematics, the board concluded that the severe weather had somehow produced an unusual event. Unusual event. That is the phrase you write when the thing that happened is not permitted by your model. They were not being stupid. They were being consistent with the best available theory, and the best available theory was wrong. Not about how waves behave on average, which it described very well, but about how often the sea does something the average does not contain. Proving that would take another 17 years, one gas platform, and an instrument nobody had installed for that purpose. Before that proof arrived, the largest ship Britain has ever lost went down with 44 people aboard, and the investigation into her would take 20 years, 2 deep ocean expeditions, and a reopened public inquiry. And the answer, when it finally came, had almost nothing to do with the size of the wave. The Derbyshire was built by Swan Hunter and delivered in 1976 as the Liverpool Bridge, the sixth and last of a class of British combination carriers. 91,655 gross tons, 169,000 tons dead weight, 294 meters long, 44 across. Renamed Derbyshire in 1978 and operated by Bibby Line out of Liverpool. She was 4 years old. In July 1980, she loaded at Sept-Îles on the north shore of the Gulf of St. Lawrence in Quebec, and what went into her holds matters more than it sounds. 157,000 tons of iron ore concentrate. Ore concentrate is dense. It occupies very little volume for its weight, so a cargo like that does not fill the ship. It sits in the bottom of alternate holds in heavy, compact heaps, with substantial empty space above it. Every one of those heaps is a concentrated load at a specific point along a 294-meter girder, and the still water-bending moment that results is the largest structural load the ship carries on any ordinary day. Her destination was Kawasaki, Japan. Sept-Îles to Kawasaki is roughly a 2-month voyage. It is an entirely routine trade, Canadian ore for Japanese steel, and it had been run thousands of times. 42 crew and 2 of their wives were aboard, 44 people. On 9th of September 1980, she was approaching Japan and ran into Typhoon Orchid. Her last known message reported that she was hove to, riding out the weather, and would be delayed. Being hove to in a typhoon is not an emergency signal. It is the correct thing to do. You reduce to steerage way, put the weather on a bearing that keeps the motion tolerable and the slamming manageable, and you wait for the system to move past. A ship the size of the Derbyshire is one of the safer places to be in a typhoon, which is precisely why the message was routine enough that nobody ashore treated it as anything else. Then, nothing. No distress call, no EPIRB, no transmission of any kind. A 294-meter ship carrying 157,000 tons of ore stopped existing between one report and the next, roughly 230 miles off Okinawa, and 44 people went with her. The absence of the distress call is the first piece of evidence, and everything after it comes back to this point. The Derbyshire had a radio room, radio officers on watch, and a master who had already been in communication about the weather. Somebody would have transmitted. The fact that nobody did means the interval between the situation becoming survivable, but serious, and the ship being gone, was shorter than the time required for a person to reach a key and send. That is a very short interval. It rules out any emergency the crew could watch developing, anything that handed them minutes of warning and a reason to use them. The searches found effectively nothing. In the immediate aftermath, some floating debris and an oil slick were reported in the general area. And that was all. The ship was in water 4 kilometers deep, and in 1980 that was as good as the far side of the moon. Then, in the years after, something started happening to her sisters. Ships of the same class began showing deck cracking in the same region of the hull, the area around frame 65 at the forward end of the engine room space, where the structural arrangement of the ship changes. That is exactly the kind of location fracture mechanics teaches you to distrust. A discontinuity, a point where the section of the girder alters, a place where stress concentrates. The most prominent case involved the Tyne Bridge, an earlier sister, which developed serious deck cracking in North Sea service. That produced a theory, and it dominated for the better part of 20 years. The Derbyshire, it was argued, had suffered a structural failure at frame 65, a crack initiating at the discontinuity and running, splitting the ship, explaining the speed, explaining the silence. The theory was coherent. It fitted the evidence available. It also happened to be wrong. And the way it was proved wrong is one of the most impressive pieces of accident investigation in maritime history. In 1987, a formal investigation was held into the loss. Its conclusion was that the Derbyshire had probably been overcome by the forces of nature in Typhoon Orchid. Read that as the families read it. Overcome by the forces of nature is not a finding. It is the absence of a finding, dressed as one. It says the sea was very large and the ship was unlucky, and it implies that nothing could have been done, that nothing needs to change, and that no one need be answerable. For the relatives of 44 people, it was an official document explaining that their dead had been the victims of weather. They did not accept it, and here is where the story stops being about metallurgy and starts being about persistence. The Derbyshire Family Association campaigned for years. They were joined by the International Transport Workers Federation, which in March 1994 agreed to fund something nobody had seriously attempted for a merchant casualty. A deep ocean search for a wreck whose position was only approximately known, 4 kilometers down, using survey technology that had only recently become capable of the job. Oceaneering Technologies ran the search. On 8 June 1994, they found her. The wreck was lying in about 4,000 meters of water, spread across a debris field roughly 1.3 kilometers long. That fact alone tells you something. A ship that goes down intact and settles is one object. A debris field over a kilometer long means the vessel came apart, and that the pieces separated during the descent, drifting differently as they fell through 4 kilometers of water. Finding her was not the end. Finding her started the argument because now there was evidence, and the evidence had to be interpreted. An interpretation of a debris field is not straightforward. Further surveys followed. The Woods Hole Oceanographic Institution ran detailed underwater work in the second half of the 1990s, and assessors from the United Kingdom and the European Commission reviewed and analyzed the collected data in 1998. What the surveys produced was tens of thousands of photographs of a shipwreck scattered across a kilometer of abyssal plain, and the job of the investigators was to reconstruct a sequence of events lasting perhaps a few minutes, from the arrangement of fragments that had subsequently fallen 4 kilometers and buried themselves in sediment. They started with the frame 65 theory, because that was the theory everyone expected to confirm. The wreck did not support it. The structure in that region did not show the failure the theory required. 20 years of the most plausible explanation, the one that fitted the sister ship cracking, the one that had a mechanism and a location and a precedent, and the physical evidence said no. What the evidence did show was at the other end of the ship entirely, at the bow. In 2000, the formal investigation was reopened under Mr. Justice Coleman, and the report that came out of it did something the 1987 inquiry had not managed. It described what happened, in order, with reasons. And the sequence it laid out is, in the most uncomfortable possible way, entirely ordinary. It begins with 2 openings in the deck, each one big enough to swallow an anchor chain. At the very front of a bulk carrier, on the forecastle, the anchor cables run down into the chain lockers through openings called spurling pipes. They are covered and sealed because water going down them ends up inside the ship. The seals are not exotic engineering. They are covers and packing maintained by the crew, checked as part of ordinary routine. The reopened investigation concluded that the seals on the Derbyshire's spurling pipes had been destroyed, and that this probably occurred before she sank. In a typhoon, with green water repeatedly coming aboard over the bow, the forecastle takes the heaviest and most violent loading anywhere on the ship. Solid water sweeping across that deck at speed is entirely capable of stripping a cover. Once that happened, water could get into the chain lockers, and from the chain lockers into the bosun's store, into the forward machinery spaces, and probably into a ballast tank as well. Not catastrophically, not fast. In substantial quantities, over time, into the extreme forward end of the ship. The inquiry also settled something the crew's families needed settled. It found specifically that the bosun's store's hatch on the foredeck had not been left unsecured by the crew, and that the officers and crew were in no way to blame for the loss of the vessel. 20 years of quiet implication that somebody aboard had failed to close something, formally on the record, removed. Now follow the water. A few hundred tons of seawater at the very bow of a 294-meter ship does not threaten her buoyancy. Loaded, she displaces close to 200,000 tons. It is a rounding error. What it does is change her attitude. She develops a trim by the bow. She sits slightly lower forward than she should. The report includes a detail that is the single most disturbing sentence in the entire document. The trim was imperceptible from the bridge. Understand where the bridge is on a ship like that. It is aft, on top of the accommodation block, roughly a quarter of a kilometer behind the bow. It is night. It is a typhoon. Visibility is whatever the spray allows. A watchkeeper is looking down the length of a deck that is repeatedly disappearing under white water. A meter or so of additional bow immersion at that distance, in those conditions, does not look like anything. There is no instrument on that bridge in 1980 that reports it. There is no alarm. There is nothing to notice. The ship was already losing, and the men running her had no way to know. What that trim did was change the way the bow met the sea. A bulk carrier's forward sections are shaped to lift as a wave arrives. Push the bow down, and she stops lifting cleanly and starts driving through instead, which means water no longer runs off the forecastle. It comes aboard, green and solid, and travels aft along the deck until it hits the first thing standing in its way. The first thing standing in its way is the number 1 hatch cover. Green water is not spray, and the distinction is everything. Seawater weighs a little over a ton per cubic meter. A hatch cover on a Capesize bulk carrier is a rectangle of steel, perhaps 20 meters by 15. 300 square meters of flat surface. Put a meter of solid water on top of it, and you have loaded 300 tons onto a panel designed to hold cargo out, not to hold the ocean up. Here is what it was designed for. Under the 1966 International Convention on Load Lines, hatch covers in the forward quarter of a ship's length had to provide a collapse strength equivalent to about 1.75 tons per square meter. Convert that into something you can see, roughly 1 3/4 meters depth of standing water. That was the international standard, agreed in 1966, applied to a ship delivered in 1976, and it was a negotiated compromise rather than a physically derived limit. Nobody in 1966 had ever measured the load a typhoon actually puts on a foredeck, because there was no instrument on any ship in the world doing that. The investigation concluded that as the Derbyshire's trim by the bow developed, green water loading on the number 1 hatch cover was accentuated, and that by about 1700 hours GMT on 9 September, the conditions had deteriorated so severely that the loading was likely to have exceeded the collapse strength of that cover. It went in. And this is the moment the ship was lost, several hours before she sank, in a way nobody aboard could have detected. Number 1 hold contained iron ore concentrate, a dense heap occupying a fraction of the hold's volume, with a large empty space above it. With the cover gone, that space filled. thousands of tons of seawater added at the front of a ship that was already trimmed forward. The bow went down further, which put heavier green water on the number 2 hatch cover, which failed, which flooded number 2 hold, which put the bow down further still, progressive, accelerating. Each failure creating the loading condition for the next one, moving aft along the deck. Once several forward holds were open to the sea, the bow simply went under, and stayed under, and the ship drove herself down. The reconstruction indicates the final phase was extraordinarily rapid. And now the silence makes sense. There was no interval in which a crew could recognize an emergency, reach a radio, and transmit, because for most of the sequence, there was no visible emergency. And when there finally was one, it lasted a matter of minutes. The debris field, 1.3 kilometers long, is what happened on the way down. A ship driven under bow first, while still underway, does not sink so much as dive, and the structure fails under loads it was never designed for as she goes. She came apart during the descent. That is why the pieces are scattered across a kilometer of seabed 4,000 meters down. So put the whole thing together, because this is the reversal that changes how you should read every other case in this story. The largest ship Britain has ever lost was not snapped in half by a wave. She was flooded from the front through a sequence of ordinary fittings over a period of hours, in whether her hull was strong enough to survive. The girder was never the problem. The girder was fine. What failed was a set of seals, and then a series of hatch covers, built to a compromise standard set 14 years before she was launched. A Sperling pipe seal costs less than a life jacket. The hatch covers were not cheap, but they were built to a rule, and the rule was the weak point. 44 people died because of a number in a convention. The Derbyshire was not an isolated event either, and this is the part the industry found hardest. Through the 1990s, the world was losing bulk carriers at a rate somewhere between 5 and 26 ships a year. Not damaged, lost. Many of them vanished in the same manner. Heavy weather, forward flooding, no distress call, no survivors. The Derbyshire was simply the largest and the best documented, and she was the one whose relatives refused to let the file close. The changes that came out of it were substantial, and they were specific. In 1997, the International Association of Classification Societies introduced a unified requirement, S21, raising the strength standards for hatch covers, with the heaviest increases applied to the forward quarter of the ship, where green water loading concentrates. The United Kingdom took the case to the International Maritime Organization and pushed for stronger covers on the basis of the investigation. SOLAS gained a new Chapter 2. Additional safety measures for bulk carriers, dealing with the survivability of these ships when a forward hold floods. And there is one regulation that came almost directly out of the sentence about the trim being imperceptible from the bridge. Regulation 1912 requires water level detectors in cargo holds, ballast tanks, and dry spaces, with audible and visual alarms, set to trigger when water above the inner bottom in a hold reaches half a meter and again at a higher level. It was applied to all bulk carriers, regardless of when they were built. In other words, the fix for a crew being unable to see the ship filling was to give the ship a way to tell them. That is a genuinely good outcome. And it should be said plainly, bulk carrier losses have declined substantially since. The system worked. Families forced an investigation. The investigation found a mechanism. The mechanism produced regulation. The regulation reduced the casualties. But look carefully at what the entire chain rests on. Every one of those new standards is a number. A strength requirement expressed in tons per square meter. A load the cover must survive. And that number can only be derived from an estimate of how much water the sea can put on a foredeck, which means the whole edifice of bulk carrier safety from 1966 through 1997 was built on assumptions about the ocean that had never been checked against a measurement. Nobody, anywhere, had ever recorded a genuinely extreme wave with an instrument. 15 years after the Derbyshire went down, on the first morning of 1995 in the North Sea, something finally did. Draupner E is not a ship. It is a steel jacket standing on the seabed about 160 kilometers southwest of the southern tip of Norway, part of a gas pipeline support complex, and it does not go anywhere. That is exactly why it mattered. Underneath the platform deck, pointing straight down at the water, was a laser rangefinder. Its job was unglamorous and entirely practical. Measure the distance to the sea surface, continuously, so that engineers could check whether the wave loads the structure actually experienced matched the wave loads it had been designed for. Nobody installed it to hunt for monsters. It was there for the same reason you weigh a truck before it crosses a bridge. On 1st of January 1995, the North Sea was running a significant wave height of about 12 meters. That is a serious winter storm and a completely normal one. The kind of weather in which North Sea supply vessels stay in port and the platforms simply carry on. Then the laser recorded a wave with a crest-to-trough height of 25.6 meters. Take a second with the shape of it rather than the size, because the shape is what made this a scientific event rather than a curiosity. The crest of that wave stood 18.5 meters above the still water level. The total height was 25.6. Linear wave theory, the mathematics underpinning essentially every wave load calculation done in the 20th century, treats a sea as the sum of many independent sine waves, and a sine wave is symmetric. Its crest is half its height. If the Draupner event had been a large ordinary wave, its crest should have been around 12 or 13 meters above still water. It was 18.5. Nearly 3/4 of the wave's total height was above the mean surface, which means it was not a big, smooth swell. It was a tall, steep, narrow peak standing over a comparatively shallow trough, and describing that shape mathematically requires nonlinear terms up to fifth order. The instrument was not malfunctioning. The platform sustained minor damage to equipment on a temporary deck, at a height consistent with the wave the laser had recorded. The steel agreed with the software. Everything changed with that record, and it is worth being precise about what changed because it was not the physics. The ocean had been doing this the entire time. What changed was that the evidence stopped being testimony. For a century and a half, the entire case for extreme waves had rested on the accounts of mariners. And mariners are the worst possible witnesses in the eyes of a scientific committee. They are frightened. They are estimating heights from a moving deck at night. They have every incentive to exaggerate, and the ones with the most compelling stories are, by definition, the ones who survived. Every board of inquiry that heard a wave described as 60 or 100 feet had a defensible reason to discount it. The München's investigators had a lifeboat with twisted pins and a wave they were not permitted to believe in. A laser has no incentive to exaggerate. Once the measurement existed, the theoretical work followed quickly, and the answer turned out to be that there is not one mechanism. There are several, and they can stack. The simplest is dispersive focusing. Waves of different lengths travel at different speeds. Long waves faster, short waves slower, so a sea is constantly reorganizing itself as components overtake one another. Occasionally, at one point in space and one moment in time, a large number of components arrive in phase. Their crests coincide, the heights add, and for a few seconds there is a wave far larger than its neighbors. Then the components pass through each other, and it disappears. That produces tall waves. It does not on its own produce the crest asymmetry Draupner showed. The second mechanism does. It is called modulational instability, and the short version is that in a steep, regular wave train, the waves stop being independent. Energy begins migrating between them. A wave that happens to be slightly larger than its neighbors can draw energy out of them and grow at their expense, and the process feeds itself. The bigger it gets, the more efficiently it steals. What emerges is precisely the Draupner shape, one disproportionate, sharply peaked crest, with suppressed waves ahead of and behind it. The hole in the sea and the wall behind it, which is what mariners had been describing all along without any vocabulary for it. The third is current refraction, which is the Agulhas machine, an opposing jet compressing wavelengths and focusing energy geometrically. And a fourth possibility emerged from later study of the Draupner record itself. Reanalysis by researchers working with meteorological archives indicated that the sea state that day was not a single wave system, but two, arriving from significantly different directions and crossing at a large angle. Crossing seas do not behave like the sum of their parts. Two wave trains intersecting can produce short-lived pyramidal peaks that neither system would generate alone, and they leave a sea surface that looks confused and behaves worse than its statistics suggest. That interpretation is the emerging view rather than settled fact, and the debate over exactly which mechanism dominated at Draupner is still live in the literature. What is not in debate is the consequence. The tail of the distribution was wrong. The models used to derive the 20-year design wave, the number underneath every hull scantling and every hatch cover standard in the world, underpredicted how often the ocean produces something far outside the expected range, which meant somebody had to find out how often. That project got its impetus from two incidents in early 2001, and both of them are unusual in this story for one reason. Everybody involved lived. In late February and early March 2001, less than a week apart and less than 1,000 kilometers from each other in the South Atlantic, two expedition cruise ships were struck by waves reported to be in the region of 30 meters. These are not fragile vessels. They are ice-strengthened ships built to carry passengers to Antarctica, operated by crews who work that latitude professionally. The Bremen had her bridge windows smashed. The wave took out her navigation and put her propulsion out of action, and she was left drifting in the South Atlantic without power. Her crew shut the electronics down and let her lie parallel to the seas for around 2 hours before attempting to bring systems back online, which is the correct decision and a horrible one, because a ship lying beam on to a heavy swell with no engine is in the single worst attitude available, rolling to the mercy of whatever arrives next, and the crew had no way to know whether the wave that hit them had been alone. On 2nd March, the Caledonian Star was crossing Drake Passage when a wave of similar scale smashed her bridge windows and destroyed navigation and communications equipment. 2 ships, 1 week, 1 ocean. Both survived. Both had officers who could describe exactly what they saw, and both produced physical damage at bridge height that could be photographed and measured. That is what finally forced the issue. In December 2000, the European Union initiated a project called MaxWave, and in August and September 2000, it did something nobody had attempted. It used satellites to take a census of the ocean. The European Space Agency's ERS-1 and ERS-2 radar satellites were tasked to record the sea surface globally over a 3-week window. They returned about 30,000 imagettes. Small radar snapshots, each covering a patch of ocean roughly 10 kilometers by 5, sampled at intervals of a couple of 100 kilometers along the orbit tracks. In 3 weeks of that sampling, the analysis identified 10 individual waves of 25 meters or more. Be careful with that number, because it is regularly misused. 30,000 small patches spread across the world ocean over 21 days is a vanishingly small fraction of the total surface area of the sea for a vanishingly small fraction of the time. 10 confirmed monsters inside that sample does not mean the ocean is full of them. It means that a mechanism which the accepted statistics treated as effectively negligible was producing extreme waves at a rate high enough to show up in a tiny sample, which is a completely different statement, and a far more expensive one for anybody writing structural rules. The measurements have kept coming. In November 2020, a buoy off Ucluelet, on the west coast of Vancouver Island, recorded a wave of 17.6 meters in a sea state of around 6. That one is not remarkable for height. It is remarkable for ratio, nearly 3 times the significant wave height, the most extreme proportional rogue wave yet recorded, and it happened in an ordinary sea in coastal waters. So the position by the early 2000s was this: the ocean can produce, without warning and without an obvious precursor, a wave 2 to 3 times the height of everything else running around it, with a crest far taller than symmetric theory permits. Capable of arriving on a ship from a direction, the officer of the watch has no reason to be watching, and the design rules that had governed ship strength for a century had been calibrated on the assumption that it could not. At which point, the shipping industry, having spent 30 years learning that its wave loads were understated, proceeded to build the largest and structurally most demanding merchant vessels that had ever existed, and to build them faster than anybody could measure what happened to them. A container ship is a worse beam than a bulk carrier, and the reason is the thing that makes it a container ship. To load and discharge boxes vertically with a crane, the deck has to open. Not partly, almost entirely. On a modern container vessel, the hatch openings can run to something like 90% of the ship's breadth, along most of her length. What remains of the deck is 2 comparatively narrow strips of steel down either side, plus the coamings that rim the openings. Go back to the girder. The deck is the top flange. On a container ship, most of the top flange has been cut away and replaced with a hole. 2 consequences follow, and both of them matter here. The first is that the hull carries a disproportionate share of its bending strength in the bottom. The bottom shell and the double bottom structure become the dominant load path, which puts enormous importance on a set of plates that spend half of every wave cycle in compression. The second is that an open-topped box has almost no torsional stiffness. Twist a closed tube and it resists ferociously. Twist a tube with the top cut off and it deforms easily. The cross-section warps out of shape, and stresses appear in places a simple bending calculation never predicts. Container ships in oblique seas, waves arriving on the bow quarter rather than dead ahead, are being simultaneously bent and twisted, and the twisting concentrates precisely where the open section has to close up again. The place where the open section closes up is the engine room. The MSC Napoli was a 4,419 TEU container ship, built in 1991, 275 meters long, registered in London. On 17th January 2007 at 8 in the morning, she sailed from Antwerp with 26 crew and roughly 2,300 containers, bound for Sines in Portugal and then South Africa. She was 16 years old, in class, surveyed, and entirely unremarkable. On 18th January, a severe windstorm crossed northern Europe. The system that killed dozens of people across the continent that week. In the western English Channel, it produced storm-force winds and seas reported in the region of 9 meters, running up the channel from the west, which for a ship steering southwest meant taking them on the bow. There is no good option in that situation, and this is a point worth dwelling on, because people assume a ship in bad weather can simply go somewhere else. The English Channel is a corridor. It has heavy traffic separation schemes, shallow banks, and a coastline on both sides. A 275-meter ship cannot heave to in the middle of it and drift because there is nowhere to drift to. She cannot turn and run because running puts her into the ports and traffic behind her. She reduces speed. She takes the weather on the bow because that is the least damaging heading available, and she keeps going. At about 11:05 in the morning on 18th of January, roughly 50 miles south of the Lizard, her hull failed in way of the engine room. Consider what that specific location does to a ship in a single instant. The engine room contains the main engine, the generators that make all the electrical power, the steering gear supply, the bilge and ballast pumps, the fuel system, and the machinery control. A hull fracture that opens the engine room to the sea does not disable one system. It removes propulsion, electrical power, steering, and the ability to pump out the water that is causing the problem, simultaneously, within minutes, in storm force conditions, in the middle of the channel. 20 minutes later, at about 25 past 11, the distress call went out. The 26 crew abandoned into an enclosed lifeboat, and this is a stage of the process that people watching from shore consistently underestimate. Launching a lifeboat from a ship that is disabled, flooding aft and moving unpredictably in 9-meter seas, is one of the most dangerous evolutions in seafaring. Get it wrong, and the boat is smashed against the hull it just left. Get it right, and you are now in an enclosed capsule the size of a bus, in the same storm that just broke a 275-meter ship, with no ability to make progress toward anything. Getting into the lifeboat is not survival. It is a change of problem. Falmouth Coast Guard coordinated the response. The assets available were 2 Sea King helicopters of the Royal Navy's Fleet Air Arm, based at Royal Naval Air Station Culdrose in Cornwall, roughly 50 miles from the casualty. 50 miles. Hold on to that number. Winching 26 people out of an enclosed lifeboat in a storm is done one at a time. The boat is pitching, rolling and yawing on 9-meter seas. The aircraft has to hold a hover above it in storm force wind, with the downwash adding its own chaos to the sea surface. The winchman goes down onto or beside a moving target and comes back up with one person. Repeat. 2 aircraft, working in rotation, in January daylight. All 26 were recovered and flown to Culdrose. Nobody died. Hold that against the München. The same ocean system, the same time of year. A ship of comparable size, 30 years apart. The wave was not the variable. The variable was that the Napoli's failure left her afloat and communicating for long enough to matter, and that a rescue base with capable aircraft was 50 miles away instead of 400. Rescue capability had improved enormously in 3 decades. What had not changed at all is that rescue is a function of distance, and distance is a function of where the ship happens to be when the hull lets go. The ship itself was not finished. She was taken under tow toward Portland, and as she came in, it became clear she was likely to break up or sink on the way. The UK Secretary of State's representative for Maritime Salvage and Intervention, the SOSREP, an office with the legal authority to overrule owners and salvors in the public interest, made the decision to put her on the beach deliberately, rather than lose her in open water. On 20th January, she was beached in Branscombe Bay, in Lyme Bay, on the Dorset and East Devon coast. That decision was correct, and it produced one of the strangest scenes in modern British maritime history. Containers went over the side, 114 of them, and began coming ashore at Branscombe. Inside were BMW motorcycles still in their crates, wine casks, perfume, shampoo, car parts, nappies. Hundreds of people came down onto the beach and carried it away, in daylight, in front of the cameras, while police warned them off. The final cost of the incident ran past $120 million. The MEB published its report in 2008, and what it found should have been more alarming to the industry than it was. The failure was not caused by the ship's material condition. It was not caused by poor construction. It was not corrosion. It was not age. It was not maintenance. And it was not the crew. It was the design. The hull did not have sufficient buckling strength in way of the engine room. There was no or insufficient safety margin between the hull's design loading and its ultimate strength, and the load acting on the hull at the moment of failure was likely to have been increased by whipping. The high-frequency vibration set off by slamming arriving on top of the wave load in exactly the way described earlier, and in exactly the region of the ship the rules examined least carefully. Read that middle finding again, because it is the one that matters. No safety margin. Not a small margin, not an eroded margin. The calculated strength and the calculated load were effectively the same number. The ship had no structural reserve at all in that location, and she had sailed like that for 16 years, fully compliant, because the rules assessed longitudinal strength most rigorously in the midship region, and the engine room is not the midship region. The investigation also weighed the cargo, and the results are their own small scandal. Around 660 of the containers stowed on deck were weighed. 137 of them, 20%, differed from their declared weight by more than 3 tons. The largest single discrepancy was 20 tons. Together, those 137 boxes were 312 tons heavier than the cargo manifest said. The Mabe was careful and correct about what this meant. The weight discrepancy was not enough to cause the hull failure. What it did was eat into the safety margin between the bending moment the hull was experiencing and the strength it had, a margin the same report had just found to be essentially non-existent. Roughly 7% of the containers were also in the wrong position or declared as something other than what they were, which the report noted was within an industry norm of around 10%. Sit with that phrase. The industry norm was that 1 box in 10 is not where or what the paperwork says on ships whose stability and structural loading are calculated entirely from that paperwork. Then came the part that turned one casualty into a fleet problem. If the Napoli's failure was a design issue rather than a ship-specific one, other ships designed the same way were carrying the same defect. Around 1,500 vessels were screened. 12 required work to bring them up to acceptable standards. 12 ships, in service, worldwide, sailing with the same structural condition that had just put 26 people into a lifeboat in a channel storm, found only because one of them broke where somebody could investigate it. And the Napoli was a 4,419 TEU vessel. By 2007, the yards were delivering ships of 12 and 14,000 TEU, and the order books were reaching further. Every one of those hulls was longer, wider, more open on deck, and calculated with the same fundamental methods that had just been shown to leave no margin at all in a region they did not look at hard enough. 6 years later, one of them broke in half in the Indian Ocean, and it did so in the middle of the ship, in daylight, where the rules were supposed to be strongest. The MOL Comfort was 5 years old. She was built in 2008 by Mitsubishi Heavy Industries at their Nagasaki shipyard, the 6th in a series of large container ships, 316 meters long, registered in the Bahamas, and operated by Mitsui O.S.K. Lines. Capacity 8,110 TEU. A post-Panamax vessel, meaning too wide for the old Panama Canal locks, built for the long-haul Asia to Europe trades where size is the whole economic argument. On 17th June 2013, she was on passage from Singapore to Jeddah with 26 crew aboard, 11 Russians, 1 Ukrainian, and 14 Filipinos. Her position was roughly 200 nautical miles off the coast of Yemen, in the Indian Ocean, in the southwest monsoon. Now the number that should stop you. The significant wave height at the time of the accident was estimated at 5.5 meters, with a Beaufort Force 7 southwesterly wind. Force 7 is a near gale. 5.5 meters is a moderate to rough sea. In the southwest monsoon, in that part of the Indian Ocean, in June, this is not weather. It is the season. Ships on that route run in those conditions for days at a time, every year, as a matter of routine. There was no typhoon, no rogue wave measured or reported, no crossing sea, no opposing current jet, no ice, no fog, and no emergency of any kind in the hours preceding. A 5-year-old ship in ordinary conditions in daylight. She broke in half. The fracture began in the bottom of the hull, amidships, and ran up the side shell plating until the girder gave way and the two halves separated. Photographs taken from the water afterwards show something that does not look like a shipwreck at all. It looks like a diagram. The bow section floating with its container stacks still lashed and intact. The stern section floating separately with its accommodation block and funnel upright and undamaged, Both of them level, both of them apparently fine, with a gap of open water between them where the middle of the ship used to be. The crew got off, all 26 of them, into 2 life rafts and a lifeboat. That deserves attention rather than a passing mention, because abandoning ship in an orderly way from a vessel that has just come apart underneath you is not a natural outcome. It requires that the 2 halves stayed afloat and reasonably stable long enough for people to reach muster stations, get into survival suits, launch, and get clear. It requires the emergency power to have held. It requires that nobody was in the wrong compartment at the wrong moment. In the München's case, in the Derbyshire's case, none of that was available. Here it was. And then they were in the water, in life rafts and a lifeboat, 200 miles off Yemen. That specific stretch of ocean in June 2013 carried a second problem that had nothing to do with structures. The waters between Yemen and Somalia were then a designated high-risk area for piracy, transited by merchant ships under armed guard, with citadels and hardened routines and naval patrols. 26 seafarers adrift in small craft in that corridor were in a situation with more than one kind of exposure, and every hour they spent in it mattered. They were recovered. Vessels in the area responded to the distress, and all 26 were picked up. No one aboard the MOL Comfort died, which is why this casualty is so uncomfortable and why it belongs at this point in the story rather than earlier. Nobody died. There is no death toll to make the point, no families campaigning for 2 decades, no memorial. By the metric that usually determines how seriously a maritime accident is taken, the MOL Comfort barely registers. Judged on what it revealed, it is arguably the most alarming structural casualty in modern shipping, because every previous case in this story came with an excuse, and this one had none. The World Glory had a gale, an abnormal wave corridor, and 14 years of service. The Schenectady had defective steel. The München had the North Atlantic in December. The Derbyshire had a typhoon. The Napoli had a European windstorm and a design flaw at a structural discontinuity outside the region the rules examined hardest. The MOL Comfort had a force 7 breeze and a 5.5-meter sea, and she broke exactly where the rules were supposed to be strongest, in the middle. The salvage attempt that followed took 3 weeks and became one of the strangest operations of the modern era. And it is worth following because it demonstrates something about a broken hull that photographs do not convey. Both halves were still floating, and both were full of cargo. Between them, they held something like 4,000 containers. The stern half contained the machinery, the fuel, and the accommodation. The bow half contained nothing but cargo and a great deal of empty steel. Salvage tugs were contracted and the operation began. And the immediate problem was that neither piece behaved like a ship, because neither piece was one. A ship is designed as a closed, subdivided, watertight envelope, cut 1 in half, and you have created an object with an enormous open end. No propulsion in one case and no steering in either. An unpredictable center of gravity, and a bulkhead at the cut face that was never intended to be an exterior surface holding back an ocean. Every wave that runs down the hull goes into the open end. The stern section held on for 10 days. On 27th of June, it began taking on water and sank. In water thousands of meters deep, carrying an estimated 1,700 containers and around 1,500 tons of fuel oil with it. The bow section was more stubborn. Under tow, it was hauled most of the way toward the Arabian Gulf. A fragment of a ship being dragged across an ocean. Half a hull with container stacks still standing on it. Then it caught fire. A container fire in a stack is one of the hardest fires in the maritime world to fight. The boxes are steel, sealed, stacked in blocks 6 or 7 high and 12 or more across, and water cannot reach the interior of a stack. On an intact ship, you have fixed firefighting systems, pumps, power, and a crew. On a towed bow section, there is none of that. No power, no pumps, no fire main, nobody aboard. It burned, and at 7 in the evening UTC on 10th of July, roughly 3 weeks after the ship broke, the bow section sank as well, in about 3,000 meters of water. The last physical trace of the MOL Comfort was gone. What remained was a question that Japan's Ministry of Land, Infrastructure, Transport and Tourism, the Bahamas Maritime Authority, and the Classification Society Class NK now had to answer without a wreck, without a fatality, and without a storm to blame. They answered it, and the answer put a specific number on how close large container ships had been sailing to the edge. With no wreck to survey, the investigators had to work the other way round. From the ship's loading condition, the estimated sea state, the construction records, the material certificates, the as-built drawings, and detailed structural modeling. The Class NK Committee on Large Container Ship Safety published its findings in 2014. The Japanese Ministry's report followed in March 2015. The conclusion was that the hull girder fracture probably resulted from buckling collapse of the bottom shell plates in way of a butt joint in the double bottom structure underneath number 6 cargo hold. In the midships part of the ship, the bottom plates buckled and collapsed first. The girder fractured afterwards, in a short time. A butt joint needs explaining because it is one of those construction details that sounds like nothing. Large ships are not built plate by plate. They are built as prefabricated blocks. Huge three-dimensional sections assembled in a hull, craned into the dock and welded together. The seam where two blocks meet is a butt joint, and it runs across the bottom of the ship. Everywhere else, that bottom plating is a continuous surface. At the butt joint, it is two surfaces joined by a weld, with the tolerances that implies a slight misalignment between the two plates, residual stress locked in by the welding, and a small local geometric imperfection. For a plate in tension, none of that matters much. For a plate in compression, it matters enormously, because a compressed plate does not fail by breaking. It fails by becoming unstable and buckling out of its own plane, and instability is triggered by imperfection. The straighter the plate, the more load it takes before it goes. The slightest initial curvature, and it goes sooner. 70 years after the Schenectady square hatch corners, the same principle in a completely different mechanism. The ship failed at the place where the geometry stopped being continuous. Then the investigators put numbers on it, and the numbers are the point of this entire section. The vertical bending moment acting on the hull at the time of the accident was estimated to have reached about 13.8 million kilonewton meters. The best estimate of the hull girder's ultimate strength, the absolute maximum bending it could take before collapse, was around 14.8 million. Probabilistic assessments put a lower bound on that strength somewhere between 12.0 and 13.0 million. Strip the units away and read what that says. In a 5.5 meter sea, in a force 7 wind, on an ordinary day, the load on the hull was around 93% of the best estimate of everything the ship had. And the credible lower end of the strength estimate was below the load. The report's own language was that when the effects of deviations in the uncertainty factors were taken into account, the actual sea state at the time, the actual yield stress of the steel as delivered, the actual as-built geometry, it was possible that the load exceeded the hull girder ultimate strength. The overlap between the strength and the load, the report said, was very narrow. Very narrow is the finding. Not a defect, not negligence, not a rogue wave. Two distributions, how strong these ships actually are and how hard the ocean actually pushes on them, sitting so close together that their edges touched, and the MOL Comfort was the ship at the point of contact. It gets worse, and this is the part that turns an accident into an indictment. After the loss, the sister ships were inspected. 6 vessels had been built to essentially the same design at the same yard, with 4 more of similar type. Buckling deformations were found in the bottom shell plating of 5 of the 6 sisters, and in one of the 4 other similar ships. Concave and convex, up to 20 millimeters of permanent out-of-plane deformation, clustered near the center line, and clustered specifically around frame 151 in number 6 cargo hold, and frame 182 in number 5, near the butt joints of the original hull blocks. The same location, the same joints, on nearly every sister ship in the class. 20 millimeters does not sound like anything. It is the width of a thumb. What it represents is a plate that has already started to go, that has been pushed past its stability limit at some point in its service, has bowed out of plane, and has stayed bowed. Because steel that has yielded does not spring back. Every one of those ships had, in the bottom of her hull, a permanent physical record of loads the design method said should not have been reaching that plate. The ships had been reporting the problem for years, in the only language available to them, and the report was written in bent steel 4 decks below anyone who would have understood it. Nobody was looking at the bottom shell plating of the center holds of container ships, because there was no reason in the rules to look there. Mitsui O.S.K. Lines' response was not incremental. The company arranged to reinforce the hull structures of those vessels to twice the level required by their classification society and adopted operational measures to reduce hull stress by adjusting water ballast volumes, twice the class requirement. That is what an operator does when it has stopped trusting the standard. The industry response came through the International Association of Classification Societies, which set up an expert group on the structural safety of container ships at the beginning of 2014 and reviewed not only the MOL comfort but a number of earlier casualties. Out of that came a new unified requirement, S11A, a longitudinal strength standard specifically for container ships, including functional requirements that the effects of whipping be given consideration in assessing hull girder ultimate strength on post-Panamax vessels. It was complemented by a further requirement, S34, dealing with the minimum loading conditions that must be analyzed. Whipping, the phenomenon described earlier, understood for decades, measured on real ships, became an explicit part of the container ship strength standard in 2015. 20 years after Draupner, 8 years after the MIB told the world that whipping had likely increased the load that broke the Napoli. That is the reversal to carry out of this, and it is not a comfortable one. The rules improved every single time, and they improved because a ship broke. Riveted crack arresters after the Liberty ships, hatch cover strength and water ingress alarms after the Derbyshire, buckling assessment outside the midship region after the Napoli, ultimate strength and whipping after the MOL comfort. Every one of those changes was correct, evidence-based, and effective. Every one of them was also written afterwards by people reading the wreckage, and ships last 25 years or more, which means that at any given moment there is a global fleet in service, fully compliant, insured, classed, and trading, built to whichever standard was current when the keel was laid. And the only way anybody will find out whether that standard was sufficient is if one of them fails in a way that leaves enough evidence to investigate. MOL took the shipbuilder to court. The insurance claims spiraled into one of the largest container casualty settlements of the era. And the question of where responsibility actually lay, design, construction, loading, operation, or the standard itself, remained contested rather than resolved. Notice, though, what every one of these fixes has in common. Hatch covers, crack arresters, buckling criteria, ultimate strength margins, ballast procedures, reinforcement to twice class. All of them are about the ship. All of them are about making the hull able to survive a load. None of them does anything at all about the other half of the equation, which is knowing what load is coming before you sail into it. That is what weather forecasting and satellite routing are for. And in the autumn of 2015, an American cargo ship with modern communications, a professional crew, and a commercial weather routing service on the bridge sailed into a Category 3 hurricane. And the way that happened has almost nothing to do with steel. El Faro was a 790-foot roll-on, roll-off container ship built in 1975, a steam turbine vessel 40 years old, operated by Tote Maritime on the scheduled run between Jacksonville, Florida, and San Juan, Puerto Rico. That trade is domestic under United States law, which means it must be carried in an American-built, American-flagged, American-crewed ship, and it runs to a weekly timetable that the supermarkets and hardware stores of Puerto Rico depend on. She sailed from Jacksonville on the evening of 29th of September 2015 with 33 people aboard, 28 American crew and 5 Polish workers riding along for conversion work on the vessel. Somewhere east of the Bahamas, a tropical system called Joaquin was doing something forecasters had not expected. Joaquin was a genuinely difficult storm, and this needs saying up front, because it is the difference between a bad decision and a stupid one. Most Atlantic systems in that position curve north and then northeast. Joaquin moved southwest toward the Bahamas, and then intensified rapidly. The track guidance available at the time diverged badly, with different models putting the storm in materially different places. Anyone making a routing decision on the evening of 29th September was working from a forecast picture that was, by the honest admission of the meteorological community afterwards, unusually poor. The master's plan was reasonable in outline. Take the direct Atlantic route past the Bahamas, pass to the south of the system, and use the old Bahama Channel, the sheltered inside route on the southern side of the Bahamas Bank, on the way back. Get under it and keep going. The alternative was to take the old Bahama Channel outbound as well. That route is protected. It is also longer, slower, and it means arriving late into a weekly liner schedule with a berth, a discharge gang, and a return sailing all queued behind you. Now the part that makes this case belong in this story, rather than in a story about seamanship. The bridge of El Faro was not short of weather information. She had satellite communications, email, and a commercial weather routing product called the Bon Voyage System, BVS, which delivered graphical weather packages showing the storm, the forecast track, and a recommended route. It is a good product. It is used across the industry. It presents the situation as a clear-colored map that a watch officer can read at a glance. The NTSB found that BVS data is, by the nature of how it is processed and mapped, about 6 hours old by the time it reaches the ship. 6 hours does not matter for a slow-moving front. For a hurricane that is moving and rapidly intensifying, 6 hours is the difference between a storm you can pass south of and a storm you are inside. And the investigation found worse. Because the vessel had received some duplicated data packages, the weather picture El Faro had the day before she sank was around 21 hours out of date. 21 hours. A ship steaming toward a hurricane, looking at a map of where that hurricane had been the previous morning. There was better information available on that bridge. The National Hurricane Center's advisories came in over the ship's satellite text and navigational warning receivers, and those were current. They arrived as plain text: position, pressure, wind speeds, forecast track, in blocks of capital letters on a printout or a small screen. No graphics, no color, no overlay of the ship's own track. Set a text bulletin against a full-color graphical map showing your route and the storm neatly separated. And human beings will believe the map. Not because they are careless, but because that is how visual information works. The most authoritative-looking product on that bridge was the least current one, and nothing on the screen said so. This is a general problem, and it did not end in 2015. Every improvement in how weather information is presented to mariners increases confidence in it. Confidence is exactly the thing that should scale with accuracy and latency, and it scales instead with graphic design. Through the night of $30 September and into the small hours of 1st October, El Faro closed on Joaquin. The voyage data recorder later established that the ship's officers discussed the weather, and that suggestions were made on the bridge about diverting. The NTSB found that bridge resource management aboard was ineffective, including the captain's failure to adequately consider his officers' suggestions, a finding stated plainly in the report, and one that has been argued about ever since, because those officers were reading the same picture he was, and the recording shows the bridge openly doubting whether their weather data was accurate at all. She passed close to the center of a major hurricane. At that point, the story stops being about weather and becomes about a series of small mechanical facts, each of which is individually trivial and which together took 33 lives. The first was a scuttle. On a ship of that type, there are small, watertight access hatches, scuttles, allowing entry into spaces below. One of them, giving into cargo hold 3, was open and undetected. In ordinary weather, an open scuttle is a housekeeping issue. In a hurricane, with water on deck, it is a hole. Water entered hold 3. Hold 3 held vehicles, lashed down. As the water rose, the cars began to float. A lashed car that becomes buoyant does not stay lashed. The lashings are designed to resist sliding and tipping, not flotation. And once the vehicle lifts, the chains go slack and the car is loose, in a flooded hold on a rolling ship. The NTSB concluded that loose vehicles in hold 3 likely struck and ruptured seawater piping running through the space, which increased the flooding, which floated more cars, which broke more piping. The ship developed a list to starboard. And here the design of a 40-year-old steam plant closed the trap in a way that nobody standing on the bridge could have anticipated or prevented. The main engine's lubricating oil is drawn from a sump in the bottom of the machinery space through an intake, a bellmouth, that has to stay submerged in oil. A ship at an angle moves the oil to one side of the sump. Beyond a certain list, the bellmouth comes clear of the surface. The pump starts drawing air, oil pressure collapses, and the turbine trips out to protect itself. The NTSB determined that El Faro lost propulsion due to low lubricating oil pressure to the main engine, resulting from a sustained list, and noted that an additional quantity of oil in that sump could have kept the intake submerged beyond 18 degrees. More oil in the sump. That is the margin. A tank level on a 40-year-old ship in a Category 3 hurricane, deciding whether the engine keeps running. Losing propulsion in a hurricane is not the loss of speed. It is the loss of heading. A powered ship can hold her bow into the sea, which is the attitude in which she takes the least punishment and shipping the least water. An unpowered ship falls off, turns beam on, and rolls with the swell. And every degree of roll pushes more water through every opening on the low side. Down flooding continued into the cargo holds through ventilation closures that were not secured. The list increased. Just after 7 in the morning on 1st October, the master telephoned the company's shore emergency contact and reported the situation. At about 20 past 7, the United States Coast Guard received a satellite distress alert from the vessel. Her last known position was around 35 nautical miles northeast of Crooked Island, in the Bahamas. At about 7:30, the order was given to abandon ship. Abandon ship into what? El Faro was built in 1975, and the lifeboats she carried were of that era. Open boats, without covers, the kind of equipment that was standard when she was launched, and which had long since been superseded by enclosed lifeboats on new construction. She kept them legally, because the requirement applied to new ships and existing vessels were permitted to continue with what they had. The NTSB was explicit about this afterwards, and its recommendations addressed it directly. An open lifeboat is survivable equipment in most conditions a ship will meet. In a Category 3 hurricane, it is a boat with no roof, in winds over 100 knots, in seas that break. Now watch the rescue one stage at a time, because this is the case that shows exactly where the limit sits. Recognition was immediate. The satellite distress alert reached the United States Coast Guard at about 20 past 7 in the morning. There was no ambiguity, no delay in interpretation, no lost transmission, no garbled Morse. Within minutes, the right people knew a large American ship was in distress and knew approximately where. Authorization and preparation were fast. The Coast Guard launched an HC-130 long-range search aircraft from Clearwater, Florida. 2 United States Air Force Hurricane Hunter air crews, already flying the storm, attempted to locate El Faro and re-establish communications with her. Travel was the first problem. Clearwater to the eastern Bahamas is several hundred miles, not prohibitive for an HC-130, which is built for exactly that, but it is not instantaneous either. And then the chain simply stopped, and no amount of capability restarted it. The position was inside a major hurricane. You cannot conduct a helicopter hoist in those winds. The aircraft cannot hold a hover. The winch cable becomes a hazard, and the downwash is irrelevant against 100 knots of ambient wind. You cannot put a cutter into that sea state and expect to find a person in the water. Probability of detection collapses when every wave is breaking and every square meter of surface is white. You cannot launch a small boat. Fixed-wing aircraft attempting to search below cloud in a hurricane are fighting turbulence and air turbulence near zero visibility and their own survival. The rescue could not begin until the weather left. That is a sentence with no technological solution. Not in 1978, not in 2015, not now. Everything upstream of it had been transformed. Satellite alerting, position reporting, coordination, long-range aircraft, a professional service with dedicated assets. All of it delivered the response to the edge of a storm and then stood there. When the search did begin in earnest, it covered thousands of square miles over several days using aircraft and cutters. What it found was a debris field, an oil sheen, containers, life rings, one heavily damaged open lifeboat, and a survival suit containing human remains. No survivors. 33 people. Set that against the München in 1978, 110 ships and 13 aircraft, an area 5 times the size of Germany. The largest search of its era. Nothing found. Set it against the MSC Napoli in 2007. 26 people, all recovered by helicopter. Everybody home the same day. The difference between those outcomes is not the quality of the rescue services. Coldros is 50 miles from the Western Channel, and the weather, while foul, was flyable. Crooked Island in October 2015 was inside Joaquin. Rescue capability is real. Rescue capability is also a function of 2 things nobody controls: how far the nearest asset is and whether the environment permits it to operate. Improve the first, and you have improved a lot. The second is not a technology problem. The wreck was found in late 2015 by USNS Apache in roughly 4,600 meters of water, about 15,000 feet. And then something happened that has no equivalent anywhere else in this story. El Faro carried a voyage data recorder mounted on the mast. In the sinking, the mast structure separated from the ship. A first mission located the recorder but was unable to recover it. A second expedition returned in August 2016 with the deep ocean remotely operated vehicle CRV-21 and brought it up from 4.5 kilometers down. It contained 26 hours of bridge audio and navigational data. About 10 hours were determined relevant and transcribed, producing a document of more than 500 pages. The longest transcript the NTSB has ever produced. Understand what that means in the context of everything before it. The München left one lifeboat with twisted pins, and her investigators had to invent a phrase for what they could not explain. The Derbyshire left a debris field a kilometer long, 4 kilometers down, and it took 2 decades, 2 expeditions, and a reopened inquiry to read it. The MOL Comfort left nothing at all. Both halves went to the bottom before anybody could examine the fracture. and the investigation had to be conducted entirely by reconstruction. El Faro left the last day of her own bridge, recorded. The NTSB published its findings in December 2017. The probable cause was determined to be the captain's insufficient action to avoid Hurricane Joaquin, his failure to use the most current weather information, and his late decision to muster the crew. Contributing were the flooding of a cargo hold through an undetected open watertight scuttle and damaged seawater piping, the loss of propulsion from low lubricating oil pressure caused by the sustained list, the subsequent downflooding through unsecured ventilation closures, ineffective bridge resource management, including the captain's failure to adequately consider his officers' suggestions, and deficiencies in the company's oversight and safety management. That finding has been argued about ever since, and the argument is worth stating rather than skipping. Voices within the industry, including experienced mariners writing publicly, criticized the emphasis placed on the master, pointing out that the same report established that the weather product on his bridge was 6 hours old by design and, on the previous day, roughly 21 hours old in fact, and that a finding of failure to use the most current information sits awkwardly beside a finding that the information system delivered stale data as standard. The counterposition is that the current data was aboard on the text receivers and was not used. Both of those things are true simultaneously, which is why the disagreement has not resolved. What is not disputed is the sequence: an open scuttle, floating cars, ruptured piping, a list, an oil intake breaking the surface, a dead engine, a ship beam on in a hurricane. Look at that chain and count how many links involve the strength of the hull. None of them. El Faro's structure never failed. She had no buckled bottom plating, no collapsed hatch cover, no brittle steel, no whipping amplified bending moment. Everything the industry had spent 70 years fixing worked exactly as intended, and 33 people died anyway, because a small hatch was open, because vehicle lashings do not resist flotation, because a sump was not full enough to keep an intake covered past 18 degrees, and because a color map on a screen was showing yesterday. That is the last reversal, and the one that reframes everything before it. The industry has spent a century making the beam stronger, and it has succeeded, genuinely, measurably, and at enormous cost. Ships are not lost to brittle fracture anymore. Bulk carriers are not vanishing at anything like the rate of the 1990s. Hatch covers are stronger, holds have water level alarms, hull girder ultimate strength is assessed with whipping considered. Every one of those improvements addressed the failure that had just happened. Not one of them addressed the thing that has never changed, that a ship at sea is a self-contained system operating hours or days from help, whose survival depends on a chain of small physical conditions, and whose crew is making decisions from an incomplete picture of an ocean that does not wait for the picture to update. There is one more mechanism, and it is the newest one on this list, and it obeys exactly the same rule as everything else in this story. In October 1998, the container ship APL China was crossing the North Pacific in heavy weather generated by Typhoon Babs, roughly 2,700 miles off the coast of California. She was a post-Panamax vessel of the C-11 class, one of the larger container ships in service at the time. She rolled violently, repeatedly, in head seas. Ships are not supposed to roll in head seas. Roll is what happens when the sea comes from the side. Going straight into the waves, a ship pitches. She does not lie over on her ear. What happened to the APL China was described afterwards as parametric rolling, and once it is explained, it becomes obvious why it took the industry by surprise. A modern container ship has a narrow waterline amidships and dramatically flared sections at the bow and stern because that shape carries the maximum number of boxes for the minimum resistance. Now put a wave crest amidships. The flared ends are over the troughs, lifted, with less hull in the water. The ship's effective waterplane narrows, and a narrower waterplane means less resistance to heeling. her stability drops. Half a wave later, the trough is amidships and the crests are at the ends. The flared bow and stern bury themselves, the waterplane widens dramatically, and her stability spikes back up. The ship's stability is now being pumped up and down, twice per wave, by the shape of her own hull. If the timing happens to be right, if the wave encounter period is close to half the ship's natural rolling period, that pumping feeds energy into any small roll that exists, and the roll grows. Not gradually. Within a handful of cycles, a ship going straight into the sea can develop rolls of 30 or 40 degrees, which puts a stack of containers 7 high through an arc that no lashing system in the world is designed for. The APL China arrived in Seattle with a substantial fraction of her cargo gone. The reported figures vary between sources, roughly 400 containers over the side. With hundreds more damaged and a cargo claim in the region of $100 million. Her operator commissioned an unusually thorough forensic reconstruction, with meteorological hindcasting of the sea conditions and physical model testing in a wave basin, and the outcome pushed parametric rolling from a theoretical curiosity into an operational reality that masters are now trained to recognize and avoid. And what is the condition that triggers it? Waves of roughly the same length as the ship. That is the third time that number has appeared in this story, from 3 entirely different directions. The maximum hull girder bending moment occurs when the wavelength matches the ship's length. Slamming and whipping are worst when the encounter is tuned to the ship's response. Parametric rolling requires a wave train that fits her. The Agulhas current's contribution is that it shortens ocean swell into exactly that band. Size is not the danger. Fit is the danger. And a ship gets longer every decade while the ocean keeps making waves of every length there is, which means growing the fleet does not escape the problem. It just moves. Which sea state is the fatal one? The ships now are enormous. The largest container vessels afloat carry over 24,000 TEU on hulls just under 400 meters long and more than 60 meters wide. 400 meters is the length that fits a wave with a period of about 16 seconds, which is an unremarkable long swell in any ocean on the planet. On any day of the year, they still lose boxes. On 30 November 2020, the One Apus, a 14,000 TEU vessel bound for Long Beach, ran into heavy weather about 1,600 nautical miles northwest of Hawaii and lost an estimated 16 containers overboard in a single event, with the damage to the remaining stacks visible from a mile away when she limped into Kobe. It was the largest container loss since the MOL Comfort broke in half, with a cargo value put at around $90 million. Everybody aboard survived. And on 1st of January 2019, the MSC Zoe, carrying more than 8,000 containers from Sines to Bremerhaven, lost 342 of them into the North Sea while passing north of the Dutch Wadden Islands. The Dutch Safety Board investigation into the MSC Zoe is the one to finish on, because it brings the whole thing back to where this started. The board found that the container losses resulted from extreme forces acting on the ship, the containers, and the lashing systems as a consequence of the specific conditions on that shipping route. In storm-force northwesterly winds, vessels there meet high waves on the beam, and large, wide container ships respond to those waves with extreme rolling. On the relatively shallow southern route, the board identified an additional risk, the combination of vertical and horizontal ship motions creating the possibility of contact with the seabed. The largest ships in the world, in some of the shallowest water they routinely transit, rolling hard enough to throw cargo off the deck, with the bottom close enough underneath them to matter. Shallow water shortens waves and steepens them. It has done that for as long as there has been shallow water. The mechanism is the same one that makes the Agulhas corridor dangerous, arriving from a different direction, and it is now being met by hulls of a size that did not exist when anybody wrote the rules about it. So where does that leave the questions this started with? Some of them cannot be answered and will not be. Nobody knows what hit the München. There is a lifeboat with twisted pins and a stowage height of 20 meters, and that is the entire physical record of the last hours of 28 men. What Dropner and Maxwave established is that a wave capable of doing that is no longer a scientific impossibility, which is a very different statement from proving that one did. The German board's phrase about an unusual event was the honest limit of what could be said in 1979, and it remains, uncomfortably, the honest limit now. The file does not close. It simply stops. Nobody will settle the world glory either. The argument between an abnormal wave and a 14-year-old hull cannot be resolved, because resolving it would require examining the fracture surfaces, and they are on the seabed off Durban where nobody has ever gone to look. 10 people out of 34 came home, and the reason the ship came apart is a matter of informed opinion. The question about whether hull strength has kept pace with hull size is partly answered, and the partial answer is the uncomfortable part. The standards now exist. Ultimate strength assessment, whipping considered explicitly, buckling of bottom panels in the middle of holds, minimum loading conditions analyzed. They apply to ships designed after they came in. The vessels contracted before then are trading today, and will be trading for years, having been built entirely correctly, to a standard that the industry's own expert group subsequently judged insufficient. And the last question, whether the crew comes back before the hull does, has an answer, and it is not the one people expect. The München? Nobody. The Derbyshire? Nobody. The World Glory? 10 of 34. El Faro? Nobody. The MSC Napoli? All 26, flown to Cornwall the same afternoon. The MOL Comfort? All 26, off a ship in 2 pieces, 200 miles from Yemen. The one Apus? Everybody. On a ship that lost 1,800 containers. Look at which ones lived. It does not correlate with how strong the ship was, or how bad the weather was, or how modern the equipment was. It correlates with one thing: whether the structure, having failed, kept them out of the water long enough for a signal to go out and something to arrive. The Napoli's engine room flooded, and she stayed up. The MOL Comfort broke into 2 halves, and both of them floated. The Derbyshire's bow went under, and she drove herself down inside minutes. El Faro lost her engine, went beam on, and rolled over in a hurricane. Survival at sea is not about whether the ship fails. It is about how long she takes to finish failing and where she is when she starts, which is the whole system, and it has been sitting in plain view the entire time. Geography sets the constraint. A shelf edge that steers a 5-knot current into an ocean swell, a channel with no room to turn, a monsoon that runs for months, a shallow route past a chain of islands. Weather activates it. A cold front off Cape Town, a typhoon south of Japan, a windstorm across northern Europe, a hurricane that turned the wrong way. Physics supplies the force, and always in the same currency. A wave that fits the ship, a bow that falls and slams, a hull that rings afterwards, water standing solid on a deck, a plate in compression that stops being straight. Human motive supplies the exposure. The Suez Canal closes, and 8 years of oil traffic reroutes past Durban. A weekly liner service needs its berth. 5 knots of free current is half a day and thousands of dollars. Nobody in this story went to sea looking for a wave. They went because that is where the work is, and the routes that pay are the routes that pay for a reason. Technology changes what gets attempted, and it changes it in both directions at once. Engines let a ship hold a line she could never have held under sail, including the dangerous line. Stronger hulls and better forecasts let operators accept conditions they would once have avoided. Enclosed lifeboats, satellite alerting, and long-range helicopters have turned casualties that used to kill everybody into casualties, where everybody walks away, and that is a real and enormous achievement. None of it moves the ship closer to the coast. Distance and environment decide the rest. 50 miles from Coldrose in flyable weather, 26 people live. 450 miles north of the Azores in a December gale, the largest search of its era finds nothing. 35 miles off Crooked Island inside a Category 3 hurricane, the most capable rescue service in the world has to stand at the edge of the storm and wait for it to leave. And the history proves it repeats. A ship at a dock in Oregon in 1943 with no wave anywhere. A tanker off Durban in 1968. A lash carrier north of the Azores in 1978. An ore carrier off Okinawa in 1980. A container ship in the Channel in 2007. Another one off Yemen in 2013 in a Force 7 breeze. Different steel, different decades, different failure mechanisms. The same shape every time. A margin that was narrower than anyone realized, a load that arrived from a direction the rules did not model, and a fitting or a fastening or a data feed that cost almost nothing and decided everything, which finally answers the question properly. A hull built to survive the worst wave in 100 years still folds in half because the 100-year wave was never the thing that was going to break it. The design wave is a statistic, and a statistic is an average of a distribution whose tail nobody had measured until 1995. The load that actually breaks ships is a sum. The still water-bending moment that was there before anyone left the berth, plus the wave, plus the whipping from the last slam, plus 300 tons of undeclared cargo, plus a plate that has been bent 20 millimeters out of true for years, arriving all together, in weather that a passenger would describe as rough. And the wave is usually not the answer because the wave is usually not the smallest part that failed. It was a spurling pipe seal. It was a butt joint between two prefabricated blocks. It was a scuttle nobody had checked. It was an oil sump that ran dry at 18 degrees. It was a weather map that was 6 hours old on the day it mattered. The ships are still out there, and they are still going the same way, for the same reasons. Off the coast of South Africa, right now, a container ship of nearly 400 meters is running southwest down the shelf edge with the Agulhas current under her, making 4 or 5 knots more than her engines are producing. She is holding the 200-meter line because the current is worth 4 knots to her and because her berth in Cape Town is booked. Her hull is flexing through the swell exactly as it was designed to, hogging and sagging, 6 or 7 seconds a cycle, a few thousand times before dawn. The lashing rods on the deck stacks tick against their turnbuckles as she works. A front is coming up from the southwest, and the swell it is pushing ahead of it has been traveling for 2,000 miles, and it is about to run into a wall of warm water going the other way. She will make Cape Town half a day early. The line she is holding is the same one Mallory drew his casualty list along in 1974, and it is still the fastest water on the coast,